All right, so then if we apply that here, does everybody agree, cross your fingers, that we could write this as the limit of x over sine x as x approaches 0 quantity squared, right? And that's a limit we know. That's 1 squared, which is 1. Okay. Again, do you have to show all that stuff? I don't know. Probably not. Probably you could just say, okay, I can see that's going to happen if I take advantage of that property of exponents and just write that as 1, right? But that's why it works. Okay. Give me 1 to 5 on that. Do you ever see why it works to get those steps? Okay. Any questions? Can I clarify any part of that for you? Yes. This one right here. Oh, okay. We haven't done that part yet. Yeah, sorry. We'll go back and fill all that in. Right. We were just taking care of simplifying this first part. Now, what about the other part? Okay, so the other part, well, why don't we, for one thing, let's just pull that negative up to the top. Multiply top and bottom by -1, so we get 1 on the bottom. So then that just becomes a -9 times the quantity cosine x plus 1, right? And now we got answers, right? Now we can evaluate these limits and be done with this problem. So this whole thing just gives me 1 squared times, if I evaluate this limit, what do I get? What's -9 times the quantity cosine x plus 1 as x goes to 0? Anybody agree? Because this is going to become 1 plus 1, right, times -9. There it is. Okay. So I'd say, again, the key step there was just recognizing that you could multiply by the conjugate of cosine x minus 1 and get that sine squared on the bottom. And then the sine squared goes with that x squared, and you're good. Sure. Okay. Do you want to see it? Does it help to, is that better if I just do that for a second? Okay, and I will post this, like I always do. I will post this on Planbook today. But if you want to, if you want to look at it or take a picture or whatever, you're welcome to always, Cor. Okay, good. All right, so then what about something like this? Okay, now this one, okay, notice here, this is kind of a different looking limit. It is indeterminate. If I try to do this one, if I let theta approach pi halves, I get 2 minus 2 times sine pi halves. Well, pi halves, that's the top of the unit circle where sine is equal to 1, right? And cosine equals 0. So I get 0 on the top, and on the bottom I get 2 plus 2 times cosine of 2 theta. Well, 2 times pi halves is pi, and cosine of pi is -1. So sure enough, I get 0 over 0, right? So keep in mind, this is almost overkill a little bit because we're going to have a much more convenient and efficient way of resolving indeterminate forms for limits later on when we know how to take derivatives. To differentiate, we can use L'Hopital's rule. But there is kind of a cool method for doing this just with analysis. This does not match either of my two standard forms, and it's pretty glaringly obvious why. Because look, both of the special trig limits are limits where x is approaching 0, not some angle. Okay, so when you see something like that, and I show this to you because this is something that it may not seem all that important to you now, but later on in life it will, when you go on and do math at the next level, do some science at the next level, and you're doing, if you're doing engineering stuff or physics stuff, you'll see things like this. This is where you'd have to use some trig identities. You're using these angle relationships, right? The sum of an angle relationship and the difference of an angle relationship. Okay, so we want to make a substitution here, right? We need our angle that we're inputting into the trig functions to be approaching 0, okay? This is a really common thing we do in math is a lot of times we'll choose to make variable substitutions in order to make an expression look a lot simpler, okay? And this goes from stuff like this, which you're going to think in a little bit is, okay, that's not such a big deal. This goes all the way on up to the most complex math that people know how to do. Like if you look at string theory math and you look at the 12-dimensional now space in which string theory is, the math is done, there are these complex shapes that sit inside this with lower dimensionalities, like a Calabi-Yau space is a 7-dimensional manifold. And a lot of times, in order to solve this brutal math that not many people could even do, I mean, there's only really a handful of people on Earth that can even do this stuff, but they have to interchange between these different manifestations of these Calabi-Yau spaces, and it's the same concept. I mean, they're just essentially making a variable substitution, only the variable is this huge animal that's really, really complicated, but it's the same idea. So you use this all the time. What could we do here? What's going to be our substitution? We need to have some angle that's approaching 0. Let's just call it x, because they're currently using a theta. How could I set up a value of x that will approach 0 when theta approaches pi halves? Because that's what our trig, special trig limits do. They approach 0. And we have indeterminacy here, right? The only way to undo the indeterminacy is to appeal to those special limits. What do you think? Okay, it doesn't need to be anything quite that complicated. We just want to come up with a little relationship that's going to relate x to theta. So I want to know, what does x equal in terms of theta, so that when theta approaches pi halves, x approaches 0. That's it, right? We could let x equal theta minus pi halves. Everybody agree then? As theta approaches pi halves, x would approach 0, right? Okay. That's our motivation for doing that, okay? And so then all we have to do is just make that substitution where instead of thetas, we're now going to use x's in our equation. So how would we go about doing that? Well, we've currently got thetas in here, so we've got to instead plug in x's. This will take you back to algebra 2. If we want to make a substitution, we have to solve for the variable that we're substituting. So we'll come down here, we're going to say, okay, well, if we solve this for theta, wouldn't theta just equal x plus pi over 2? Everybody agree? How we doing? Jeez. Wow. Sometimes, I tell you what, sometimes, honestly, especially teaching this class, it's like amazing to me that here, look at the stuff we're talking about, the high level, and then, I mean, it's just like wow. Could there be a bigger difference? Okay, so theta equals x plus pi halves. We'll make that substitution. If we do that, we're just going to make that substitution there and there and there, right? Okay, so then we end up transforming this into the limit of 2 minus sine of x plus pi halves divided by 2, well, it's supposed to be a 2 there, isn't there? 2 plus 2 times cosine of 2 times the quantity x plus pi halves. Everybody agree? All I did was I just swapped out the thetas for the quantity x plus pi halves. But look what happens to the value we're approaching then. As theta approaches pi halves, x approaches 0. That's important, right? And now we just have to simplify that whole thing, which is, I mean, it's just a bunch of trig stuff. And I know that's probably, you tell me, how do you feel, how comfortable are you with your trig identities? 5 meaning I feel like I know these things so well. 1 meaning I don't even know what a trig identity is, or somewhere in between. Okay, because that's, I mean, I might even have, because we got to practice that a little bit. That's something that I think is, I mean, like you all want to be, if you're taking the AP test, that number needs to be a 5, which isn't a big deal. Trig identities are easy. It's no big deal. I mean, you just have to practice a little bit. Practice doing some stuff like this, though, where you're going to do some transformations involving properties of trig functions and trig identities. So maybe we need to do take a pause and do a little practice assignment on that here real soon. Okay. I mean, yeah. I feel like, would you want to do that? Okay. Yeah. So let's do this then. So we could rewrite this as the limit of 2 minus 2 times. Now, what's the sign of x plus pi halves? Well, here's one of our trig identities we have to use. That's like saying the sign of a plus b, where a is x and b is pi halves. And so this is the trig identity that goes with that. Okay. Right. Now, here's how I remember these. Because I mean, again, I don't generally go home and just study my index cards at night, but there's a way that I can always sort of remember this stuff, because I know these. I know the double angle formulas, and you guys probably know those too. We use those all the time, right? Sine 2x is 2 sine x cosine x. Okay, that's one you just that's one you got to know. We'll use that one all the time. So how am I going to get that from sine of a plus b? Well, that means that I'm going to have two terms that add up here, right? In this case, it's x plus x. So I should have a sine times a cosine plus a sine times a cosine. A's and B's are both x's, so they end up being like terms, right? I get sine x cosine x and cosine x sine x, which are the same thing. So I know that this has to be additive, and I have to be multiplying a sine times a cosine to get that, right? That's kind of how I think about that. And what about the other one? Well, I know cosine 2x is cosine squared x minus sine squared x, which I could convert using my Pythagorean identity into either one of those if I want to write it in terms of cosines or sines exclusively. But we'll just leave it like this: cosine squared minus sine squared. So there's a minus sign in the middle, which means I know that the plus and the minus have to get flipped, right? Because when I'm adding angles, I'm subtracting terms, and I know that the cosines have to go first because I'm getting cosine x times cosine x, and the sines go second. And so you can always kind of reverse engineer that. It takes 10 seconds to do, but then I don't have to waste those brain cells memorizing all that stuff, right? You can just kind of derive it as you go. And if you're doing it a whole bunch, you'll just remember them anyway, right? Okay, so what do we get then? If we do this sine of a sum, right? Sine of x plus pi halves, isn't that going to be, by this top identity, I'm going to get 2 times the quantity sine x cosine pi halves, which is what? Top of the unit circle, cosine's x coordinate, 0. There you go, right? So that one we already know is going to 0, plus cosine x sine pi halves, which is what? 1, right? So that one goes to 1. And then on the bottom, we've got 2 plus 2 times cosine, and let's simplify this, 2x plus pi, right? Did I write that down right? Yeah. Okay, 2x plus pi. Okay. So I've got to do the same thing to cosine 2x plus pi. So let's rewrite that in green here. If I use this identity, the cosine of 2x plus pi is going to be cosine 2x times cosine pi, right? So this part right here is going to become cosine 2x cosine pi, which is just -1, right? Minus sine 2x sine pi, which is 0. So then what's that take us to? On the top, we've got 2 minus 2 times, this whole term went to 0. So really I've just got minus 2 times cosine x, right? Okay, that's what that whole top becomes. Give me thumbs on that. Do I need to pause for a second? Okay, that's a lot of stuff coming at you. Let's go back and look at this numerator again for just a second. How did we get this? We just applied that identity, right? Where a is x. In fact, let's write that down. A is x and b is pi halves. And we're just using that one, right? Okay. So we had sine A cosine B plus cosine A sine B. But that's the first term goes to 0. Yep.
I feel like the only thing that makes it really confusing is that there's a lot going on that fraction thing. If only like we were able to see it, like just pretend you ignore the 2 minus 2 and you just focus on the sign.
Yeah, okay, so let's circle the sign stuff. So everything in here becomes this. Right? Okay. And everything here, where is it? Everything here becomes that. Okay. Does that help a little bit? Right. And then, so now we got to rewrite the whole thing. I didn't even bother with the 2 plus 2 times that stuff. I just wanted to focus on making the transformation of the trig stuff. Right? Okay. And look what happens in each case. One of the two terms in our trig expansion goes away. Okay. And so we end up with, on the top then, we've got 2 minus 2 times just this term right here, which is a cosine x. Okay, and let's circle that in yellow. So the only thing remaining from all the yellow stuff was that cosine x. Okay, on the bottom, we've got 2 plus 2, the cosine of 2 times the quantity x plus pi halves. We got just this stuff on the bottom, right? Only thing that remained was cosine 2x times cosine pi, which remember is -1. So that whole thing just looks like okay, so here's everything from that green bubble ends up there. That's it. Okay. So this is a kind of a nasty problem, isn't it? I mean, you're going to like L'Hopital's rule a lot better. But it's really good to just exercise your brain and go through some problems like this where you got to follow lots and lots of steps. The more you do that, the easier it gets. Okay. So let's then, on the top, we've got 2 minus 2 cosine x. That one's fine. On the bottom, we could pull that negative out front. And cosine 2x, remember, we could write that if we wanted to as, how do we want to do this? We want to write that as, say it again. That's cosine squared minus sine squared. Okay. That's what this is. Cosine 2x becomes cosine squared x minus sine squared x. So on the bottom, we're going to end up with 2 minus 2. We'll take that 2 out front. And then that stuff inside just becomes cosine squared x minus sine squared x, which we could write as 2 cosine squared x minus 1. I'll show you how I got that. That's just taking this guy and rewriting it like that, changing this 1 minus cosine squared. Okay, and making that substitution. I used this guy right here. Yeah. Okay. And then now what do we end up with here then? So we've got, I pulled the negative, I pulled that negative out there in front of the 2. Okay. Okay. And 1 minus cosine x over, so where are we going with this now? I'm trying to figure out where we're going with this. Let's see. Four cosine x minus, okay, I see. Yeah. So then, so 2 minus 2 cosine x over. Now, what am I going to get on the bottom if I distribute that negative 2 and combine like terms? 4 cosine, I'm going to get 2 minus 4 cosine squared x plus 2, right? Everybody agree? Isn't that the same thing as 4 minus 4 cosine squared x? Because that's my identity, right? Because I'm saying cosine of 2x. This part, man, I'm getting so many colors in here. That part, that blue part, is the same as that blue part then, right? Okay. Right? And now this is starting to look a little bit better, isn't it? I could factor a 2 out of the top and a 4 out of the bottom and make that a 1/2, right? Okay, hold that question for just 1 second, Jonathan. So I'm going to get, on the bottom, I'm going to get a 2 times the quantity 1 minus cosine squared x. On the top, I get 1 minus cosine x. And you guys could tell me what that is. 1 minus a over 1 minus a squared is what? I'll give you a hint. 1 is the same as 1 squared. That's the same thing as 1 minus a times 1 plus a, isn't it? Right? See what I'm getting at? And so the 1 minus a's are going to cancel. Right? And so let's write that out. And look what I did. I didn't write my limit there. Here I always tell you guys to write your limit. I just get so excited by all that math that I forget sometimes. But if we rewrite this whole limit, then let's show the cancellation. Oh, and there's a 2 on the bottom, right? There's a 2. Okay, does everybody see how we went from there to there? Give me thumbs on that. Does that make sense? Just factor the bottom. Okay. Now, the indeterminacy is going away, isn't it? Right? Because as x goes to 0, these are the factors that are causing the indeterminacy. How about that? Okay, so we should be able to cancel those and evaluate our limit. Now, when we let x go to 0, we just get 1 over 1 plus 1. Oh, and there's a 2 on the bottom. Sorry. Right? 2 times quantity 1 plus cosine x. And so I get 1/4. That's it. I should feel like dropping my pen. Yep. Okay, I just combined like terms. I distributed the -2, which gave me a -4 cosine squared x plus 2. 2 plus 2 is 4. Okay. Maybe I shouldn't have skipped that step. I just felt like I was running out of board space. So here, let me give you a little. So all we did here. Okay. Okay. Good. Okay. Yes. Yeah, you bet. You bet. Do you want me to do this? Or is that too small? Is that good? Okay. The right here, because sine of pi is 0. See, look where that is on the unit circle. Think where that is on the unit circle. So here's my unit circle, right? It's right for you guys. It's right there, right? Yeah, right over there. For you guys, is it over here? No, for you guys, if I draw the circle, is that right? Oh, you're right. Yeah, it's over here. You're right. Gosh, yeah, over here. Right. So then that's the y coordinate on the unit circle. The sine of theta is the y coordinate of the point on the unit circle. So when it's on the x-axis like that, it would be 0. Does that make sense? Okay. Other questions? Yes. On which step here are you talking? Like down there? Right here. Yeah, I did. I just factored a 2 out and factored a 4 out and made it a 1/2. Right? Okay. Again, maybe I skipped too many steps there. Let me make a note of that. So from here, okay. Yes. Mm-hmm. Okay. Why that's the only thing left? Because cosine of pi halves is 0. So that one goes away. Sine of pi halves is 1. So I end up with 0 plus cosine x times 1, which is just cosine x. Okay? Okay, makes sense? Yeah, sure. Oh, this would be a hard one. That'd be a really hard question. Yeah. Okay, and I promise you, I will post this on there. Better show your parents, challenge your parents to do that one. See if they can do it.